Welcome, everyone. We are honored to have Professor Jonathan Claussen among us today, the third presenter of the William Penn Leaders Speak series. Professor Claussen holds a master's degree in mechanical engineering and a PhD in biological engineering from Purdue University. He further continued his research at major East and West Coast universities before coming back to his Midwestern roots at Iowa State. Here, Professor Claussen directs a high-impact presidential initiative in translational health areas. His research is very relevant, rather in the front and center of STEM education and training, especially in nanoscience and engineering. So without any further ado, I would like to present Professor Claussen to our Penn community. And my STEM friends, please help me welcome Professor Claussen.
Thanks so much for the introduction, and yes, it's good to be back here in the Midwest, especially after this nice winter we just had. It actually does remind me of growing up in northern Wisconsin, though, so it wasn't too bad for me. I thought it was a decent winter. So yeah, today I'll talk about nanotechnology and how to use nanotechnology, and especially some of the materials that are used to make all sorts of different devices, and how these types of materials that are nanostructured can open up new avenues of research and new avenues of technology. We'll focus in on graphene, but I'll also talk about thermoelectrics a little bit and how we can make flexible thermoelectric generators. So just to give you a little bit overview of my group, here's a little bit older picture of my group, but right now we have about 7 PhD students, a postdoc, our master's student just graduated, and we always have several different undergraduates working in the lab at once. A lot of our projects are biosensing related, so we work with, for example, oral cancer detection in saliva. We monitor pesticides and fertilizer detection in soil slurries. So that first oral cancer project was funded by the Roy J. Carver Charitable Trust. The second projects are funded by USDA and NSF. We work with stress monitoring in sweat through the Federal Highway Administration. Salmonella detection in meat products is funded by NSF, and cattle disease biomarkers in serum, it's by a Canadian consortium, including Alberta Milk. So we make all of these sensors based with nanomaterials, primarily graphene, and then we're also starting to develop various energy harvesting devices. So that's kind of an overview of the lab. And then I'll kind of go into some of these materials we have. Now, I am in the mechanical engineering department, and some of the stuff I'll talk about today might not seem so mechanical engineering-ish, but that's kind of how nanotechnology is. When you're working with small-scale materials, you often have to learn the chemistry that's involved to synthesize those materials, so you can structure them and make them in the way that you want, and then you can apply applications that might be a little bit more pertinent for engineers. So with that said, let's go into some of the materials we're using, such as graphene. Why use this material? Researchers have found there's been a Nobel Physics Prize just in 2004 about really reinventing or refining graphene, or isolating a single monolayer of graphite or graphene and understanding the material properties, and that's what those physicists did. And we found out that it's incredibly strong. It has 200 times the tensile strength of steel, so you could pick it up if you could make a single sheet large enough. It has ballistic conduction, million times higher current densities than copper, for example. It's elastic, it stretches up to 20% its length. So in theory, if you had a 4-kilogram cat sitting on a single layer monolayer of graphene, it could sit on a 1 meter squared of that material if you could hook it up that way, which we're not quite there yet. It has the highest thermal conductivity known of any material. It's almost pretty much impermeable, so even small helium atoms can't squeeze through the carbon lattice. And it's really transparent. A single monolayer you couldn't really quite see. It doesn't really absorb much light, only about 2%. So what we're trying to do is, take kind of this wonder material, harness those incredible and significant material properties, and make them into devices and technologies that we can use. And in particular, biosensors is what our field focuses on. So when I was doing my PhD, I used to grow these nanomaterials, carbon nanotubes and graphene. So carbon nanotubes are just, if you think of the monolayer, a single layer of carbon is graphene in a 2D sheet or a plane. You roll that up into a tube, that's a carbon nanotube. If you have multiple layers, and it's rolled up into a tube, that's a multiple layer carbon nanotube. So they're made very similar. All these nanomaterials typically in a chemical vapor deposition tube furnace. So this is a high temperature tube furnace up to 1,000 degrees Celsius, a vacuum chamber environment. So that can be kind of expensive and costly. And so you need to grow these on materials. Graphene is typically grown on a copper foil, or you have to have some sort of metallic seed catalyst, such as iron, nickel, or cobalt, where those carbon will start to grow from. And those are metals that are typically have to be evaporated or deposited on a material such as silicon, ceramics, or glass that can withstand that tube furnace, that high temperature. And then researchers typically have to use photolithography to pattern that metal to figure out where you want those carbon nanomaterials. If you want to make a transistor in a certain location, you need to pattern that. And that involves a clean room processing technique. That's expensive. So all of these products then have to be done on a rigid material, such as silicon, ceramics, or glass, and so forth. So that works well if you're trying to make a new computer chip and put it into your computer, and you're working at Intel. But if you want to do things that's flexible, that's maybe can conform around a pipe, that can go on the body, then doing those processing isn't really going to help you. And these processes are typically low yield and expensive because of the equipment and so forth. So what we're trying to do is take those materials, those nanomaterials, synthesize them a little bit differently. We chemically exfoliate flakes from graphite and make it into inkjet printable ink. And of course, when we print it, and then we print it and can make these flexible electronics. It's not as pristine as a CVD grown graphene. It's not a single layer. It has defects in it and material grain lines that will impede electronic and thermal transport. But we can still retain fairly good material properties, and we can have it behave like a printed liquid metal. And what that allows us to do is to make these devices very cost effectively. It's amenable to roll-to-roll manufacturing. And we can print them on paper, textiles, foils, or what have you. So it really could be a degradable and disposable electronic, and it's still just carbon. So there's no precious metals involved, no gold electronics that you would need, such as are typically used in computer chips. So it's a really cost-effective method, and kind of opens up a new avenue of research and products. If you think about having bendable, flexible electronics on a flexible polymer or flexible paper, you could start putting them into clothing, so wearable devices, lightweight military devices, some sort of integrated health monitors. Some people are integrating them with, on top of the body, on the surface of the body, but also inside the body to make measurements and so forth. Also bendable solar materials and so forth. So really, as those manufacturing processes, those costs go down, our applications definitely can go up. So we really see this as kind of an avenue to bring nanotechnology to the market, whereas before it was kind of impeded or stunted by its cost and its limited use in terms of carbon-based electronics. So here's a little video. Yeah, we're going to get this started for you. So this is a video that's showing we've printed a polymer underneath, and then in this case we've spin-coated a layer of graphene flakes on top of this, and that's the black that you see on top of this white polymer, and that's a bath of acetone, and we're mixing it around. And it might be a little hard to see, but that does not say William Penn, that says ISU. It's a cyclone, it's the cardinal for ISU, that's psi. So it's just kind of to show you how easy it could potentially is to make these types of circuits. What's kind of interesting, this technique that we figured out, is that we're patterning the polymer underneath, kind of just like a photoresist that you use in photolithography. And then we're coating it with graphene. So that acetone has to go through that flake layer, that black flake layer that was on top, hit the polymer underneath, etch off or react with that polymer where it is, and then lift off the graphene that's on top of that. And then wherever that polymer wasn't underneath, the graphene that was on that backing substrate stayed there. So it's kind of a unique little process that we did. And this is that technique. We print a polymer mask. It's kind of like an acrylic, kind of like a nail polish-like substance. We spin coat graphene. We optimize kind of the post-baking process, the process so that the graphene that wasn't on top of that nail polish-like substance stuck and didn't come off, but the nail polish-like substance still was able to etch away. And then we bath sonicate it or rinse it off in that sonicate bath or acetone bath that you saw. So doing that, we can make electronics. So this is a silicon wafer in the back. But we've made all these, what's called an interdigitated electrode. It just has two finger-like combs that are coming together and creating a type of circuit that works well for biosensors. And we're able to get down to line resolution to make those little finger combs about 20 microns. And that's really good because that's, photolithography can get a little bit lower than that, a few microns in line width, but not too much lower than that. And we didn't have to do any clean room processing, so it's a pretty inexpensive technique to do. And we can control the layer thickness by spinning on more graphene and so forth. So it's just a fabrication technique to make these type of electronics. So after you were to, let's say if you were to inkjet print that graphene, aerosol print the graphene, or do this kind of spin coating technique, you notice that graphene layer, those graphene flakes, aren't really that conductive because it's still embedded in them to make them stick to that surface is an ethyl cellulose. It's a non-conductive binder. There's some solvents in there and so forth. So typically what researchers have to do is they have to do some sort of annealing process. And what's conventionally been done is thermal annealing, which is done at about 200 to 300 degrees Celsius. But of course you can imagine if you were to deposit or print that onto a paper substrate or a polymer, that's just going to burn up in that oven. So what we came up with is this rapid pulse laser technique. It doesn't harm the underlying paper or polymer substrate, but it anneals that top layer of graphene enough so that it carbonizes that ethyl cellulose, makes it conductive, burns off any remaining solvents, and then it can also nanostructure that surface a bit, kind of roughen it up, so to speak. So that's relatively flat with a low laser energy, but then these particles kind of stick up and start getting etched into a bit as we increase that laser power. So after we do this laser processing technique, our sheet resistance of that electrode goes down by almost 3 orders of magnitude. So it's about 25 mega ohms, and now we can get it per square, and we can get it down to about less than 20 ohms per square. So that sheet resistance is similar to what we would see if we printed silver ink or metal ink. Those are a little bit lower than that, but we're getting pretty close. So basically now we're taking really cheap carbon flakes, these kind of graphene flakes, printing them, laser treating them, and now it behaves almost as electrically conductive as a printed metal would. But what's also neat about this is we can also pattern into it with that laser. So that surface topology we could make, they kind of look like these pyramid-like structures. That supplies incredible amount of surface area, which is really important for catalysis, such as you need in electrochemical biosensing. But also, we can make it in a way, we can pattern that surface so that the graphene can turn into a surface that's non-wettable or super hydrophobic. So when we first print it, it's generally hydrophilic. Surface water contact angle would be around 45 degrees. When we treat it correctly with the laser, we can get that close to 155 or 160 degrees. So it's a super hydrophobic surface. So now that you have a non-wettable surface, that could be used for a lot of things. Maybe this is a surface you would put on an airplane wing to help it de-ice or prevent ice buildup. Or maybe it's put into a biosensor where you don't want biofouling to occur or other things to collect on that surface, and it'll stay clean. So that's kind of a neat material property that we can do just by patterning that surface. And all of this is done, of course, on a flexible electrode, but that patterning of that surface, making that surface it can make the surface electrochemically active as well. So we have all that surface area. It's good for catalysis, and these are just kind of cyclic voltammetries in an electrolyte, a ferrocyanide probe. And we just kind of get shapes that we'd expect for a platinum wire that was in a vial as well. So it's behaving potentially as a good sensor, and we're doing hydrogen peroxide sensing here at different concentrations. And all we're just showing in these graphs is that at lower lasers, we don't really see really the peaks, the oxidation peaks or the redox peaks that you'd expect from an electrochemical sensor, but when we ramp up that laser, it starts becoming the bird-like peaks that we'd expect from redox reactions. So it's becoming more electrocatalytic and a sensor that is useful for biosensing. So we learned a few things that we needed to not only print it right and print it with high resolution, but treat that graphene surface in a way so that it would be electrocatalytic. If we were to dig down a little deeper and look into the material analysis of what we actually have on that surface. So this is just Raman spectroscopy. I won't go too much into that, but we have a DG and 2D peak. For graphene, you'd expect to see all three of those peaks present. When we don't laser anneal it, we don't have the 2D peak, but when we do laser treat it, we start seeing that 2D peak. So it's becoming more graphene-like, so to speak. And we think that those grain boundaries are starting to stitch or weld together, and it's becoming more of a continuous layer of graphene after we've done this laser treatment. So that's kind of a little bit background on the material properties and what we can, how we can manipulate that to make it a better catalyst. And here I'll go over a few of the things we can do with that. After we've created that graphene, we've patterned it, we've made it more electrocatalytic with the laser, then we functionalize it with a biorecognition agent to make it selective to an analyte in solution. So in that first slide, I talked a little bit about how we detect certain biomarkers in saliva or looking in food products for Salmonella. Well, one of the things that what really allows them to become selective toward those analytes is our biorecognition agents, such as an enzyme. So a diabetic test strip to do glucose monitoring typically has an enzyme on it. Glucose oxidase or glucose dehydrogenase selectively binds to that glucose in that droplet of blood and converts it into an electroactive species that electrode can monitor. If you don't have that on there, then your sensor won't selectively bind to the glucose. You won't selectively measure what you're after, in that case, glucose. And there's all different types of biorecognition agents. There's enzymes, there's antibodies, aptamers, and so forth. In this case, we are working with collaborators from the U.S. Naval Research Laboratory who made a specific enzyme that attaches to a pesticide, to a nerve agent, organophosphates. So this type of a pesticide can break down an organophosphate into an electroactive species, and that electroactive species can oxidize on that surface of the graphene and then give us give us electrons that we can measure and then correlate to the concentration of pesticide in solution. So we immobilized this enzyme on that surface, and this was a graphene surface with platinum nanoparticles. So we just peppered it with a few small particles that are around the diameter of about 20 to 25 nanometers in diameter to make it even more electrocatalytic. And then we tested this pesticide in various solutions. And our results showed pretty good stability. I'll just highlight a few of these results. So we showed, pretty good activity of the enzyme, retaining almost 80% of its activity after several weeks. Times tested. What's nice about enzymes is you can test them over and over again. An enzyme breaks down its substrate, and then it's ready again to bind to a new substrate, so you can reuse those sensors. And then it's highly selective. So we tested it against other insecticides and different herbicides in a solution, and they gave minimal interference. So that was a good selectivity test. In all, what we wanted to do is, you'd expect these pesticides to be high in a farm field, but as they trickle down into the water supply, could you monitor them in the drinking water if they got in there? So the EU directorate has about a drinking water limit of 1 nanomolar concentration. In our detection limit, we got pretty close to that. So ours is there at the bottom in red. This is one of our graphene electrodes, and we got a detection limit about 3 nanomolar. So we wanted to improve that a little bit to get down to the 1 nanomolar detection limit. And one of the ways that we did that was introduce a little bit of a new technique into the manufacturing of these electrodes. So in this case, we took salt, it's a porogen, we could put it into the ink itself, and then when we laser treated it, those salt would break open and kind of leave the surface of that graphene, but it would leave behind it these kind of big craters on the micron scale. They're not so big, I guess. Nothing is really big what I'm doing. So that opened up a lot more surface area. Now we have these larger micron craters that are larger than those smaller nanoscale flakes. So we just added a lot more surface area. We were able to bind an enzyme to that surface and do the testing, and we were able to get the detection limit under a nanomolar just by tuning that surface. So that just kind of shows you, just by making these small tweaks to the fabrication process, you can really change the electrocatalytic ability of these nanomaterials. So that was a case of enzymatic biosensing with pesticides. We also can do, and those kind of sensors are really just a test strip. In our case, we just use, it's kind of a simple design electrode. I don't know if I've got a picture of it here. Yeah, it's more just kind of this is the working area right here. It's a circle, and this is the contact lead up to it. So there's no really intricate geometry involved in that circuit. But for immunosensing, that's when we immobilize an antibody onto the surface of these electrodes to detect antigens of interest that might be in solutions. We want a different type of circuit because we want to do impedance spectroscopy. So that's where we have those fingers where we need the high resolution. And that technique where we did the spin-coated graphene in the lift-off method, that had allowed us to make electrodes that were suitable for antibody sensing. And we're working with collaborators to do salmonella sensing and detection in, for example, this was a case in chicken broth where we could detect a certain species of salmonella down to about 30 CFU per mil. We're getting closer to 5 CFU per mil. Ultimately, we want to detect 1 CFU per mil, or 1 viable bacteria per milliliter of solution. And this would be kind of an amazing step because we all know about the food recalls that we've heard in the news, whether it be different types of foodborne pathogens from E. coli to Salmonella to Listeria. And if you could do this affordably at really low cost, then food processing facilities could actually implement these sensors on a much wider scale and test product quickly. This test only takes about 15 minutes. Where right now, if they were to test for bacteria, they usually do plate counts or have to incubate that bacteria and run an ELISA kit. And that incubation of that bacteria can take 12, 24, even up to 2 days in order to get enough bacteria for that sensor to be sensitive enough. But since our sensor's already very, very sensitive, we don't need to do those incubation processes. So we could do ours in minutes. And that could be the time that it takes for that food to come out of a processing line, get tested, and then go on a shelf. Where testing before is just so long that a lot of times it's just not economically feasible to test all of this product and wait before they ship it out. So that's an example of the type of immunosensor that we're doing. So I mentioned too that we were working with fertilizer ion detection, and this is a little bit different type of graphene. So this is called laser scribed graphene. So we take Kapton tape, which is polyimide, and we're able to convert that structure of carbon, it's sp3 to sp2 hybridized carbon, which is what's found in graphene, just by treating it with a laser, much like the laser that I'd mentioned before. And that gives us, that kind of burns or chars that, or really changes the carbon into that structure that's conductive. And we can make electrodes out of this now and functionalize it with an ion selective membrane, for example, so that we can measure things such as nitrate and ammonium in water samples and in soil to get really a picture of how much fertilizer runoff is going into the soil, how much fertilizer is there, to help the farmer know, could I spray fertilizer intermittently throughout the season when needed instead of dumping it all in the beginning of the season and hoping it lasts? So intermittent spraying throughout the growing season could prevent a lot of runoff and could potentially prevent our algae blooms that we see in our lakes and waterways. So that's a project that we're working with, and we have a soil column here in the lab, and we're actually testing it or comparing it to, a standard probe that you can buy. So if we were to buy like a nitrogen probe right now, it can cost $500 to $800 a probe, where these sensors themselves are like less than $1 each. So they might not be right now exactly as robust as those, but we're getting there, and we're getting pretty close, so we can get a really cheap alternative. So you imagine if they're much cheaper, you could start putting these out into the farm field and mapping out nitrogen levels at different points in the farm field and getting a better picture, maybe using machine learning or artificial intelligence to help tell you, where in the field you should put that fertilizer, and pinpoint that for you. These are just some of the tests so far. This is just a test strip that we can monitor cyclic ups and downs, higher and lower concentrations of both ammonium and nitrate, which are both important to getting a good feel for the total nitrogen content in your soil. And at detection limits that we would, very low detection limits, lower than we expect to see even in soils. So that was kind of the fertilizer and the pesticide sensing. And then we talked about pathogen detection. But now we've also used that same graphene that we've printed onto different substrates in that kind of finger comb-like structure, the interdigitated electrode. And since it's just carbon, it's very biocompatible. So we can actually grow cells on these circuits, and they like that surface too, because they like that rough microstructured surface. And we can electrically stimulate them so they can, if we put stem cells on them, they can transdifferentiate into different lineages. So this was a case where we teamed up with a collaborator at ISU, Dr. Mala Pragada, to make these kind of nerve conduits to embed nerve cells into breakpoints of a nerve, peripheral nerves, and hopefully help regenerate that nerve. And this is, of course, a huge issue, especially with warfighters coming back from the battlefield, having nerve injuries to civilian nerve injuries as well. So we take that, that same kind of interdigitated electrode surface. In this case, we mobilize stem cells on them. We showed that if we applied this voltage to them intermittently throughout the day and over weeks, we could help them transdifferentiate into Schwann cells. And typically what researchers would have to do is to help this transdifferentiation process from occurring is to put nerve growth factors on them and chemicals to help that process. But this is a chemical-free process, just purely through electrical means. So you could really imagine now that you have this graphene circuit, you can roll it up into a conduit, it's biocompatible, you could potentially put it in the body, you could stimulate these nerve cells without having to put any nerve growth factors, other chemicals in there. So you could truly help, it could truly be an in vivo in application for this. And this is just some of the other data, just showing that if you just take one of the outputs of this transdifferentiation process is NGF, nerve growth factor, and it just becomes the highest for those that have been electrically treated stem cells on the graphene versus typical chemical stimuli or no treatment at all. So and this is a cell here on that graphene that just is growing on that surface itself. So that was kind of all the graphene research and carbon nanomaterial research. And then to end the talk, I'll just briefly talk about kind of our latest research on printed thermoelectrics with nanomaterials. So what we want to do here is take flexible, kind of the same aspect, making flexible electronics, but making thermoelectric generators. And thermoelectric generators convert heat waste into electricity or to power. And typically they're bulky, they're big, and they're put on applications where there's a really high temperature gradient, like satellites in space, where it's really cold there, but the satellite is hot compared to the atmosphere, so that you have enough heat drop in order to get meaningful electricity. But we're trying to make them low cost, highly efficient, and potentially used on everyday products, like in a coffee cup or on the body, for example. And here's one of our samples, our first prototypes in the lab, where we're printing these black substrates wires here. Are actually telluride-based nanowires. So bismuth telluride and lead telluride, that forms the P and N junctions for this thermoelectric generator, and this is liquid metal that's been printed on top of it. And we can wrap this around a wire really tightly, and it doesn't crack, it doesn't break. We put a polymer on top of this so it doesn't oxidize either. So it works quite well. Here's some of the factors that is involved, the figure of merits. If we looked at the ZT value, that's just the value that shows how efficient it is. So thermal conductivity is in the denominator. You want to decrease that for these materials, and then you want to increase the Seebeck coefficient and the electrical conductivity. So those are some of the parameters that we're looking at and trying to increase that. And we can do that in a number of ways using these telluride-based nanowires. They have low thermal conductivity and a high electrical conductivity. So they're unique. They're kind of unique semiconductors in that way. And we do things such as changing the thickness of that electrode. We could increase phonon boundary scattering, so we could decrease kappa or decrease the thermal conductivity. So all those kind of different types of parameters we're looking at. But then we also, just like with the graphene electrodes, we anneal those substrates so that the morphology of it changes as well. After we do annealing, you can really see it here in C and D, where the nanowires are printed here, and then they just look like they're kind of morphed together. And they kind of helps them sinter them. And this sinter effects, increase the density of the film and makes it a better thermoelectric material. So all of these, this is just an example, putting it around a cup, different temperature gradients in that cup where the liquid might be hot or really cold. and then generating power from that cup. That's all we're showing there. So from this kind of device there's 5 little individual thermoelectric generators, we could power like an LED out of this. Ultimately, we'd like to scale this up and start powering sensors that we might put on the body or other meaningful things. You could operate this in reverse and through the Peltier effect and give it power to also cool down things. So you could imagine if you made these potentially underneath body armor for a soldier or police officer, you could help cool them down and supplying that power. Whereas other cooling sources, generally don't last very long, like an ice pack or what have you. But this could be a continuous way to cool something down. It's small, it's flexible, it could fit into uniforms, etc. Yeah, so this is kind of neat. This is our last design that we're trying to make. So, if you wanted to do something 2D that's amenable to roll-to-roll manufacturing, you 2D print it onto a surface. This is called kirigami, which means paper cutting. So we print it on 2D, but then we'd cut the polymer around it in a way so that when you flexed it, like this, these thermoelectric devices pop up in a vertical direction so that if you put it around a curved surface, like this is a bottle, but if you put it around a pipe or your arm, that 2D structure then become 3D, and these surfaces would vertically touch that surface. So now that's kind of how you want it, thermoelectric generated, because you want the hot source. This pad here needs to be on that hot surface below, but you want these tips farthest away because you want those in the cold area or the environment. So you want to try to maximize that thermal gradient. So you want to try to get as far as you can from that surface so you can get to the atmosphere. So this is a way, kind of a neat little nifty way to do that. So that's something that we're working on right now. And you can see it here stretching. Here's that surface. We stretch it out, and then these little surfaces fold out and become kind of vertical to it. So just by, making a structure, paper cutting, so to speak, taking that same idea and applying it to thermoelectrics, we can make a device that might be useful and affordable. And here's kind of the temperature gradient. You can see we're looking at 100 degrees to 40 degrees Celsius. Okay, so I think I went, yeah. So that was my talk today about nanotechnology and some of the materials that we had. Thank you for your time. Hopefully I didn't bore you too much, but I'd love to take any questions you have.
One of you engineers ask something.
Yeah. Okay.
So often you see on like Hollywood movies, you see stuff about nanotechnology, and what, if anything, is kind of the coolest thing that you've seen on the verge of nanotechnology that you just find interesting yourself?
Probably all my research, because it's so cool. No. But yeah, no, I know Hollywood always talks about nanobots and like these little robots that are going to go into your body and do all of this. And I actually worked for a researcher, or with a researcher who kind of made these particles that could travel. But I mean, on that scale, you couldn't, because of optics, you couldn't put little cameras on bots. It's really not like that. So I'd like to first state that it's kind of overblown. But I think what's neat about nanotechnology is that it's really more about how you can tailor materials to make them have new properties. And I know that sounds probably really not that cool, like nanobots, but that makes all new avenues of things possible. Because, just taking graphene, it is the most thermally conductive material that we know of. If we could just harness that, we could use that for a lot of different applications. If we could really start controlling where we grow carbon nanotubes on a chip, we could make a transistor that's smaller than the transistors we have today, and we could follow Moore's law, and chip design could get smaller and smaller, and you could have smaller and smaller devices. From cooling electronics to making thermoelectrics to making better biosensors, these materials could really improve the speed and performance of almost all the products we have. We just have to find a way to make them scalable, because a lot of times it's made in small batch processes that's just too expensive for industry to adapt, and make it and that's pretty much it. And so therefore then we could introduce them into products. The health concerns with nanomaterials, just being small particles, potentially passing the blood-brain barrier. Those are issues I think we can work out, but nanoparticles are prevalent throughout the atmosphere already. So there's generally more scare out there than there should be, I think. I don't know if that answered your question.
You talked about how you're injecting the materials into inkjet printers and
Yep.
printing them. Do you see a future or where this becomes more consumer based, where people could potentially print or design their own circuits?
Yeah, absolutely. So, I mean, they're already trying to make, with like 3D printers, like the spools, embedded with some of these nanomaterials to try to exploit their material properties. And that's kind of the wave, right, of new processing, where everyone potentially could have a 3D printer. You would just purchase the intellectual property, so to speak, of a new design, and then you'd have the spool, the nanomaterial that would go in there, and you could print it. So I could see piggyback kind of the new wave of printing technology and manufacturing. Yeah.
This idea of using these nanomaterials to generate electricity is kind of interesting. And so I guess my question is, what kind of surface area would you need? I'm sure it kind of depends on the temperature difference, right?
Yeah.
But to generate a substantial amount of energy, I mean, give us kind of an example of, what kind of surface area you might need and what you could do with that energy.
Yeah, no, that's a good question. So that one device that I showed, it's pretty crude, and it didn't have the Kirigami structure, but it was printed and it's 2D, and we could light up a LED light, a small one, with that circuit, with I think it was about a 20 degrees Celsius temperature drop from the hot source to the cold ambient. So yeah, it definitely depends upon that temperature gradient. So if you had a really high temperature gradient, you'd need a lot less material to potentially make it into a device that's efficient to get electricity from it. But we can do things. We can make fin-like structures. So I didn't show it on here, but a lot of these carbon nanotube forests that we have, the incredibly amount of surface area, and we'd put that on the cold plate or the cold side of the thermoelectric, and that would help cool that surface really rapidly to significantly enhance the thermoelectric generation from that surface. So there are other ways, not only the thermoelectric materials that make those PNN type legs of the thermoelectric generators, but also putting nanomaterials on those cold and hot plates to conduct electricity a lot better, and to have like a fin-like structure to cool it off faster. So those are all places where those materials can be incubated. In terms of having, it's hard to say on what temperature gradient, what surface area you would need, but that's something we could definitely look into more. Yeah.
Are these printed circuits are clean enough to make transistor parts? Yeah, they can be commodity parts of the computer.
Yeah, that's kind of what we've had some of my collaborators work at IBM Watson and research labs in upstate New York, and they're trying to make these circuits. They want to grow them, that carbon nanotube exactly where they want it. On a surface, and they need to put a source and a drain on there, so they need to have metal contacts to them. The issue of that is just trying to grow that, and if they can vertically align them, then they can stack them a lot closer together, or on a 2D plate or surface. But then they have to have the bottom metal contact and the top metal contact. So I think all of that still is challenging, and that's kind of where. But if we can figure out exactly how to place those carbon nanotubes and grow them or synthesize them in the exact location on a 2D planar surface, then they would be there. That's still a challenge, though. Yeah. All right. Sounds good.